Right, so I want to quickly talk you through this assignment. As you can see, for this assignment, we have two things that you will be submitting. One for the temperature, one for the heartbeat. For the temperature, the two files are the Asc file and also the Python file. So our simulator will take your Asc file, give it to LTSpice if you've installed LTSpice in the proper place on your hard drive, simulate it, use the output, which is stored in a raw output file by LTSpice, convert that to a list in Python, and then we give that list to you in Python. We called it Amplitude, and you have to convert that amplitude to a temperature in a temperature variable, which will be returned to the operating system. Hopefully you have used the template we've given you. I'm just, while I'm speaking, showing you, I've redrawn mine in the template. Hopefully you haven't tried to use your previous assignment Asc files and convert that into something that looks like the template. I'm definitely expecting you to redraw it, otherwise things will go wrong. So just redraw your circuit in LTSpice, and that should be sufficient. Right, so what you can see here is the Asc file. This is just a very simple design that I used to set this up, and this is obviously then in the folder that you received from us. You can see that's the file there. And what we need to do now is first to just check that this whole thing works. I used the PW input file that I got for that I had for my the first submission on assignment 1, and I just populated these with my normal values, and I made a file called temp sensor PWL. There we go. So now I know if I just consider my circuit here, you can see temp sensor PWL is what is read in, and I have control over that. So if I just simulate this, at least I can see whether it works or not. Right, and then I can check it. Is everything as I expected? Seems to be. There we go. Okay, so I've just given it a few steps, and you can see it simulates properly. So now at least I know in this circuit and in this folder, I know that the circuit's working. So if there's a bug, I know it's not with the LTSpice file, and I know that because the Python just calls the LTSpice, it should work. So I'm just going to close this for the moment. Let me also just say, sorry, while I was debugging this, while I was trying to ensure that this is working, I just used the normal DC source here to power the temp sense, just to be sure that everything was working. I was just applying a low temperature, a middle temperature, and a high temperature so that I could see that it's working without the PWL file. But now I've got the PWL file running as well, and now I can actually close this, and I can close this CSV file of mine. So now I'm back here, and now considering that simulation generated a few things. I don't know if you realize this, but this raw file that I'm indicating here, this is the output. If I go and look at this, it is the actual output. There's a bit of a header there, and then it's the raw dump of my data. There we go. That's the raw dump of the data. The first bit is preamble, and this is essentially what the Python is intercepting to check with the output of your circuit. But it's going to generate that for itself. So I'm going to delete those two files. You can see they've recently been generated from that simulation. So I'm just deleting those. There's no interference from the LTSpice whatsoever. And I need to then just pay attention. This temp sensor PWL, this is obviously the one that I've just generated. If I now go to Python, and you can see the path here is the same path as I have here. So I'm in that directory, and I can then go, let's go for 38 for now. So 38 is nice in the middle. Right, so I can set the temperature to whatever I want here. That is what is returned. So let's just see what happens. So if I run it with my input conditions, so this is the temperature sensor specification, and this is the temperature at which I want to simulate it. So 500 millivolts offset, 10 millivolts per degree Celsius, and then the 38 is just the temperature that I wish to simulate. What it's going to give me is, hopefully in a second when it's done, it should give out the 999 that I told it to give out. Just jumping back here, you can see temp sensor PWL has been updated, and if I just look at what's inside, you can see this is just the 880 millivolts. Where does that come from? Well, I told it to run 38 degrees, and 38 degrees is right slap bang in the middle of my sensor specification. My sensor specification is for 500 millivolts and 10 millivolts per degree, which gives you 880 millivolts for 38. That's all it is. So it's told the simulation use 880 millivolts. As you can see, it has now spat that out at 999. So what you need to do is you need to use this vector. It's called the list in Python. You need to use this list to generate the output. So the first thing I want to show you to try here is using that amplitude, you can then plot what comes in. So all I've done here is I've included an additional library called matplotlib as PLT. So this is going to be my plot tool. And then I've also included something I'm going to use a bit later. But what you can do is, if you just want to see what's going on, you can tell it, could you please plot time versus amplitude? So just to see what's going on. And then just to take it one step further, you can also print the len of amplitude. So that should then tell us what the length is of amplitude. And let's just change this quickly to make it, just give me the final value of amplitude. And let's rather return that to the console. So I'm just going to run this again. And now you can see it went much faster. It realized that it did not have to simulate because the raw file and the Asc file dates were compared, and it said, I don't need to simulate again. Nothing has changed in the Asc file. Now it plots out. I can see this is my response to that input. Value is at around 2.2 volts, which is what is expected for the circuit that I've drawn up. And if I close it, it spits out 2.2. So 2.2, it's obviously not 2.2 degrees Celsius, but it is 2.2 volts output. And you can see here the output is after 2 seconds. So it's 2,000 samples. As I said, I wanted to print out how many samples there were, so it prints out that 2,000. And then what I can now also do is I can do different things with this temperature. Obviously, I can take this a bit further. Instead of just printing the code, or at least the final value, I can print the mean. You can see I've included the mean function here. I can print the mean, and then I can also use that mean and send that back. So all this is doing is it's taking the average, the mean of the final values of amplitude from the 20th last one up to the last one, taking the mean and returning that as temperature. So if I do that now, it's going to do the same type of thing. It's just when it returns, it's going to give me a mean of all the previous samples. So the only thing left for you to do is to calculate this calibration constant. So how am I going to calculate what the actual voltage was? So I've done some calculations for my circuit here, and if I apply the math here, I'm just going to take away the plot to save some time. If I then execute this, and remember, it's very important, save this Python. So after you've printed the mean, you can also then use that mean as the V out. So I've made a V out mean is equal to that. And then you need to figure out what is the calibration constant. So first you do it analytically, and then you can go and twiddle with it or do it empirically. Analytically means you do the calculations. The one that I'm showing you on the screen now is the calculation, but you can also then do what we call calibrate, where you do a few samples, you measure them, and calculate a transfer function between input of the sensor and output of this transducer of yours, or this sensing system of yours. So if I run this now, I'm just going to give it a 38 again. You can see it gives me 38.028 is the temperature. If I do it for 34, it has to resimulate now, because the ASC file is older than the raw file. Because I've changed the input, it has to resimulate it. Well, and it gives me 34. Now, obviously, as I said, this is an analytical solution, so it's not going to be perfect. I'll have to calibrate that out, and I'll tell you in a later lecture how to do that. Doing it for 42 degrees, and as you can see, after it's simulated, it gives me 42 degrees as an output here as well. There we go. So it's 2000 samples, the output voltage is 3.88 volts, and the temperature is 42 degrees Celsius.